What we're going to be talking about today are the various circuital laws that we will use to analyze circuits in this class. Or at least we will be if my stylus will start writing. Try this again. So the first law that we're going to talk about is Ohm's law. It's very likely that you guys are already familiar with this, but we're going to go into a bit greater detail about some nuances that we're going to see in this class. So way back in the early 1800s, a German physicist named George Simon Ohm ran a series of experiments. And what he did was he found out that for any circuit or network that was a two-terminal network, which I'm going to represent by a black box here. So we have this black box network representing a system under test. We don't particularly know what's in it, what components are in it, or anything like that. But what he found is that if he excited this system using some sort of source, does not matter if it is a current source or a voltage source, if he measured the voltage drop across the terminals, I'm going to call that V test, and the current flowing into the terminals, which I'm going to call I test, he noticed that these two quantities were proportional to each other. And so he developed the relationship R, the resistance of the system under test, is equal to the ratio of the test voltage to the test current. So from this relationship, we can see that the units of resistance are volts, the unit of voltage per amp, and we call this an ohm, which has the symbol of omega. Okay. So there is one thing that I want to point out here. The direction of the current flow and the polarity of the voltage are important, right? So in your previous classes, you probably learned that V is equal to I times R, which we could absolutely get by algebraically manipulating this relationship that we have here. But in this class, we're going to need to pay extra attention because we're going to be following the passive sign convention. So if we have a resistor, and this is the schematic symbol for a resistor, which you're likely familiar with. So if we have some resistance R, and let's say that the voltage drop across our resistor has this particular polarity, and the current flowing through our resistor is in this particular direction, so that the current is flowing into the positive polarity terminal, then we will express Ohm's law as the voltage drop across the resistor is the current flowing through the resistor times the resistor value. However, if we have the opposite case, where the current is going to flow into the negative polarity terminal of our resistor, like so, we are going to have to use the negative version of Ohm's law. So VR will be equal to negative I times R. So to reiterate here, whenever the current is flowing into the positive polarity terminal, the voltage drop is simply I times R. Whenever the current is flowing into the negative polarity terminal, we need to include a negative sign in our Ohm's law formulation. We can actually develop a second constant of proportionality for this system under test as well. This is what's called the conductance G, and this is simply the ratio of the test current to the test voltage. So it's nothing more than 1 over R. The units of conductance are amps per volt, which we call the Siemens, named after a different German engineer. This is the same Siemens that started the Siemens Electronics Company, and this has a symbol of S. So using conductances, which have the exact same symbol as a resistor, if we have some conductance G and the voltage drop across our conductance has this polarity and the current flowing into our conductance has this direction, then effectively a different formulation of Ohm's law dealing with conductances gives us I is equal to V times G. And if we have the case where the current is flowing into the negative polarity terminal, we will need to include a negative sign. So these are our relationships for conductance. Now, in this class, and honestly in most electrical engineering classes, it is very rare that we actually use conductance. I didn't start using it regularly in my electrical engineering academic and professional career, excuse me, until I started working on transmission line systems where the conductance is used to account for leakage currents flowing through a dielectric medium. Okay, so the overwhelming majority of the time, particularly in this class, it's going to be easier on you if you effectively neglect the concept of conductance entirely, and anytime you see a conductance, and you'll know you see a conductance when it's listed as measured in Siemens, you simply take the reciprocal of that conductance value and then treat it as if it were a resistor, and then you can go on about your day. So I would argue that for the overwhelming majority of cases, and practically all of them in this class, simply treat your conductances like it's equivalent resistance, and then you can go on about your day. While we have these expressions given, we can develop a few more by introducing our power relationships, right? So in our last class meeting, we said that the power absorbed by an element was equal to the voltage drop across the element times the current flowing through the element. And then it mattered whether or not the current was flowing into the positive polarity terminal or into the negative polarity terminal. Well, with these relationships and using Ohm's law, if we have P is equal to, PR is equal to VR times IR, we are going to get, if we substitute in VR as IR times R, we are going to have IR squared times R, or alternatively, substituting IR as VR over R, we would wind up getting VR times IR is VR squared over R. For our conductances, excuse me, that should be a P, not an R. We're going to have V times I, which will come out like IG squared over R, excuse me, over G. And VG times IG also looks like VG squared times G. So these are all the different types of relationships that we are going to see for or different ways to express Ohm's law on the left-hand column, and then different ways to calculate the power for both resistances and conductances. So let's talk a little bit more about these concepts of resistance and conductance. Okay. So resistance is a measure of how difficult it is to pass a current through a particular medium. So effectively, the larger the resistance value is, the harder it is to pass some fixed amount of current. Conductance is the exact opposite. Conductance is a measure of how easy it is to pass a current through a particular medium. So the larger the conductance, the easier it is to get current to flow. As you can probably guess, both resistance and conductance have a dependency on the type of material that we are trying to pass current through. But what may be surprising is that there's also some dependence on the geometrical shape of the object that we're trying to pass current through as well. So dealing with resistance, we can say that the resistance of a particular object is given by rho sub E times the object's length divided by the object's cross-sectional area. So this rho sub E is what's known as the resistivity of the object, and it is a material property. This resistivity is measured in ohm meters. Then we have our length, measured in meters. And here we have our cross-sectional area, measured in meters squared. And so algebraically, it should be easy to see how the units come out to give us ohms here, right? So I was asked a question yesterday at the end of the class about voltage drops over long sections of wire. And so we're going to talk about that more formally here. So let's say that I have a section of wire, and it's very long. Let's say, for example, that its length is 10 meters. Okay. And let's say that the diameter of this wire, D, is equal to 1.024 millimeters. This would be typical of AWG, or American wire gauge, number 18 copper wire, which is very similar to the wire that you guys used in your kits and in the freshman series. Okay. Copper has an electrical resistivity, so I'm going to have rho Cu. So the resistivity of copper is 1.68 times 10 to the -8 ohm meters. And if we use this resistivity value and the geometrical properties of our wire, let's figure out what the resistance of this 10-meter long section of wire is going to be. So the resistance of our wire is going to be 1.68 times 10 to the -8 ohm meters times our length of 10 meters. Because we're given the diameter, we're going to use pi over 4 times the diameter squared. So here we have pi over 4, 1.024 millimeters squared, and then a conversion factor. There are 1,000 millimeters for every meter, and I need to square this conversion factor. And what I'm going to wind up getting as the resistance of this 10-meter long section of wire is 0.204 ohms. Okay. So let me ask you guys a couple of questions here. Okay. The first of which is, how long is 10 meters of wire compared to the length of the wires that you guys usually use to set up a simple circuit?
It's much longer.
Much, much longer. Typically speaking, I would argue that unless you're, I actually can't even think of a reasonable reason to do this. Typically speaking, if you're setting up a circuit, at least in this class, the wire length that you're going to be using is probably less than 2 to 3 inches, right? And 2 to 3 inches is significantly smaller than 10 meters. So if the length is much smaller, what would we expect the resistance of a short run of wire to be?
It would be lower.
Exactly right. So if the length is smaller, the resistance is smaller, okay? So for AWG number 18 wire gauge, if we use something, so let's see, if it were 1 meter, it would be 0.02. If it were 10 centimeters, it would be 0.002. So it would be roughly 2 milliohms of resistance for something that's 10 centimeters long, which is about 4 inches, give or take. So, okay. What was the smallest resistor that you guys used in your previous classes? Anybody remember?
5 ohms? No, that doesn't sound right. Like,
Was it 220?
So in the Engineering 120 series, to make your LEDs shine the brightest without burning them out, you would usually put either a 220 ohm resistor or a 470 ohm resistor in series with your LED. That would give you the brightest amount of shine, or the 220 is technically a little bit brighter. You get the brightest response out of your LED without running the risk of accidentally burning it out by passing too much current through it. So generally speaking, we are going to be using resistances on the order of tens to hundreds of ohms. How does a 10 to, let's start with a 10 ohm resistor. How big is a 10 ohm resistor compared to the resistance of this 10-meter long wire? What's 10 over 0.2?
Like 5?
10 over 0.2 is 50, right?
Oh.
So we had a 10 ohm resistor, and then we had a 10-meter long section of wire. The resistance of the resistor is still 50 times larger than the wire. Well, what do you think is going to happen when we use short sections of wire? The resistance of the actual resistor is going to be significantly larger than any amount of wire that we're going to use in any practical sense. So I'm bringing all of this up because we can see very clearly here that real wires absolutely do contribute some resistance to a system. But for the purposes of this class, we're going to ignore it because it's so small in comparison to the size of the resistors that we're actually going to be dealing with. And that's largely going to be the case in the overwhelming majority of practical applications that you're going to deal with and face as you go out into industry and start setting things up. The only time you're ever really going to need to pay attention to the resistance of a wire is when that wire is going to be carrying a very large amount of current. Because if you pass a large amount of current, even through a small resistor, you can still see an appreciable voltage drop. So for those of you that go into like a chemical plant or something like that, and you're working on setting up, let's say, HVAC systems for a new building or something like that, you want to make sure that your cable runs to your compressors and things like that are as short as they can be so that you don't have an appreciable voltage drop over those conductors, and so that the compressor of your HVAC system actually sees the nominal voltage that it's expecting. If you run it at a lower voltage, it can actually cause damage to the compressor motor over time. But other than things like that, where you have things that are consuming large amounts of power because they draw large currents, the size of the resistance, or excuse me, the resistance of the wires is fairly inconsequential. All right, so we've talked a bit here about the concept of resistance. Let's talk a little bit about what resistors do. Anybody have any ideas?
they lower the voltage so that other components can like handle the voltage appropriately.
You're close, but you're using the wrong word there. They limit the current. That's so.
Yeah.
If we looked at your LED circuit that you guys built numerous times in your 120 series, you had something like this. You had a 5-volt supply from a digital output of your Arduino board. Then you had a resistor, typically in the ballpark of 220 ohms. And then you had your LED and your ground. This is your LED shining light because things are on, right? What would happen if you didn't include a resistor in this circuit?
then the LED would get too much current and burn out.
Exactly right. Yeah, it'll shine really brightly for
Second.
about half a second, and then it will never shine again because you've literally passed so much current that it is burned out. 100% correct. So the principal role of resistors is really twofold. It's two ways of looking at the same thing, okay? A resistor is used to limit current, and it does this by converting electrical energy into heat, okay? So how many of you guys as parents own an electric stove?
I have one myself.
You have one yourself, even better. So do you know what the heating element of your electric stove looks like?
I've seen one before. This is like a brand new electric stove. It's like a glass surface, but I know there's like a heating element underneath. It's like a coil,
Yes,
like
absolutely.
thing.
It's a coil type shape. So I'm going to attempt to very crappily draw one here. It's going to be something like this. So you coil it around several times, and then you wind up passing that coil underneath like so. So these are the terminals of your coil. Why do you think the coil is shaped this way?
For the same reason that the cable, like the longer it is, the more resistance it has. And so I think whenever you put it in a coil like this, the current has to travel further in a material with a high the value you had, like the material value. I forget the name of it already.
The resistivity.
Resistivity has a high resistivity, but then when you pass a lot of current through it, it has a long way to travel, and so then it heats up as a result.
Exactly right. Yeah. So the reason that the coils in your ovens are shaped like this is to make it as long as possible while taking up the smallest amount of space. And you want to make it long so that it heats up a lot. You've absolutely nailed it. How many of you guys have space heaters?
I happen to own one.
Yeah, so a space heater, the heating element is just really a section of what's called nichrome wire. It's a really thin wire that can handle a lot of current before it melts. And so you take this really thin wire and you wrap it around all over the place numerous times, pass a current through it, it starts glowing red hot but doesn't melt, and then you use a fan to blow the heat off of the wire, and that's how you heat your room. It's all the same thing. It's just using the material property of the medium. So nichrome or whatever the heck an oven heating element is made of. And then you make it really long so that the resistance is high, and then you force current through it and it converts electrical energy into heat. That's all a resistor is capable of doing, is converting electrical energy into heat energy. And sometimes we use that heat for specific purposes, okay? All right, so I think we have a pretty good idea of what's going on with resistors and the concept of resistance. Like I said, for the most part, anytime we see a conductance, our life will be easier if we just take the reciprocal of that conductance and then treat it as if it were a resistance. So unless anybody has any questions, Dave Lewis says space heaters are the #1 cause of house fires. He is not wrong, at least anecdotally. Definitely an issue that needs to be paid attention to. That's why so many of them come with modern safety switches, but even those can fail. We can go on a long rant about that, but let's move on to other things.
Okay, I just have a small question for the resistivities. Are those going to be like in the problem, or should I like remember a few?
I was introducing that purely to talk about why we are going to neglect the resistance of wires in this class. So
Okay.
You'll, for the most part, never see that again, actually.
Okay, fair.
Yeah, so in the Engineering 120 series, you effectively made an assumption that wires don't have any resistance. I wanted to show you why that assumption is valid.
Okay.
Yeah, so you will be provided any constants and things like that that you would need. I wouldn't expect you to remember the electrical resistivity of copper. I don't, and it's in front of me somewhere. So,
Okay.
All right. So, any other questions about Ohm's law and resistance before we move on? All right. So, we are now going to talk about, let me think which one I want to do first. Let's do Kirchhoff's voltage law first. So this is the second of the three laws that we're going to be talking about today. Kirchhoff's voltage law effectively states that the sum of the voltage drops around any closed path. I'm going to underline this because we need to talk about it in a moment. Must be equal to 0. You may have heard it described in your Engineering 120 series as the total voltage rise in the circuit must equal to the total voltage drop. It's the same thing. Effectively, if we have a simple circuit here, so let's say that I have a voltage source, let's call it a 10-volt source for the sake of argument. And then I have a resistance. The value of the resistor isn't particularly important, but I have measured that there is a 5-volt drop across this resistor. And then I have another resistor, and I'm trying to determine the voltage drop across this resistance with this particular polarity. And then let's throw another source in here just to make things a little bit more interesting. That's something that's going to be significantly different in this class than your previous classes. We are going to be dealing with multiple sources, both current and voltage on a lot of occasions, instead of just having one battery or something like that powering our entire circuit. So for a simple circuit like this, and by the way, this is an example of a single loop circuit. All that means is everything is in series. My penmanship is getting terrible here. So whenever we have a single loop circuit like this, Kirchhoff's voltage law is usually a good place to start trying to analyze things, okay? So if we were trying to solve for this unknown voltage VR, we could write a Kirchhoff's voltage law equation around this loop, and we'd find that VR is the only unknown voltage that we have, right? So I'm going to detail to you guys how I write my KVL equations. The first thing that I do is arbitrarily pick a direction for the current, okay? And it really isn't a current, like it's not necessary that a current is flowing. I'm just actually trying to decide which direction around the path I'm going to write my equation. So for this particular circuit, we could choose to go clockwise around this path or counterclockwise around this path. Anybody have a particular preference?
I like clockwise.
Clockwise, okay. Chat says clockwise as well. So I am just going to make an indication that we are going around this path in a clockwise direction. I typically start at the bottom left-hand corner. And whenever I see a negative polarity terminal first, I give that voltage a negative sign. And whenever I see the positive polarity terminal first, I give that voltage a positive sign. So using that convention for this particular single loop circuit, I would have, and I'm going to write KVL here just so you know what we're doing, negative 10 volts because we see the negative sign first, plus 5 volts because when we're looking at the 5-volt drop, we see the positive polarity terminal first, minus VR because we saw the negative first, minus 3 volts because we saw the negative first is equal to 0. And then I can algebraically rearrange this thing. So it looks to me like negative VR is going to equal to 10 volts plus 3 volts minus 5 volts. And therefore, VR is negative 8 volts. So we've just applied Kirchhoff's voltage law around this loop to solve for an unknown voltage. So before we work another example, it's a little bit more difficult. Does anybody have any questions about how I wrote that equation?
I mean, just like an observation. So you start in the bottom left and you just work your way around, and then you enter each value with its appropriate sign sequentially, and then you solve. And that, right?
Yeah, that's it. Just a simple formulaic approach.
Yeah, okay.
Where the direction that we choose to go around our loop literally doesn't matter. As long as we put positive signs when we see the positive polarity terminal first and negative signs when we see the negative polarity terminal first, it does not matter which direction we choose to go around any particular path. Okay. So let's look at another example. And what we're going to do here is we're actually going to tie Ohm's law into our analysis as well. Okay. So this is the circuit that I want us to analyze. Let's make this a 60-volt source. A 30-ohm resistor. I'm going to put a dependent source here. Let's make this, sorry, I should put that second thing vertically so it's easier to see. Let's make this 4 Vx. Let's have a 15-ohm resistor here, and I'm going to define Vx as the voltage drop across the 15-ohm resistor with the positive polarity terminal on bottom. And my goal here is to determine the following two things. Okay. So I want us to determine the value, excuse me, this menu could go away, of this current. I'm going to call it IA. And I also want us to find this voltage, VB, which is the difference in potential between these 2 points in our circuit. And the reason why I'm trying to have us solve for this quantity VB is so that I have an excuse to talk about this concept of a closed path that I underlined up here. Okay. So this is a single loop circuit. So we are going to use Kirchhoff's voltage law as our first place to start, okay? So because we have a specific current that we're trying to solve for, and that current is flowing around this loop in a clockwise direction, I'm going to use that direction to write my KVL equation. So if I write my KVL equation for this circuit, what should my first term be?
Negative 60 volts.
Negative 60 volts, absolutely correct, because we see the negative polarity terminal first. So now we have a little bit of a problem, okay? Because we weren't given the polarity of the voltage drop across the 30 ohm resistor. So we have to assume one, okay? It is impossible to make the wrong assumption here, as long as we wind up applying Ohm's law correctly here in a couple of moments. So do you guys want the positive polarity terminal of the voltage drop across the 30 ohm resistor to be on the left or on the right?
Left.
Okay. So I'm going to write V30 here. So this is the voltage drop across the 30 ohm resistor, positive polarity terminal on the left. Once you do this a few times, you won't actually need to specify these things. You'll kind of get into the habit. But right now, while we're learning, I'm going to be very meticulous about things. So since we are assuming the positive polarity terminal for the 30 ohm resistor is on the left, what should our next term be?
Positive 4 volts.
So plus V,
Oh, plus. Yeah,
because
sorry.
that's the next voltage we see,
Yes.
right? Okay. What's our next term look like?
Then it would be positive 4 volts.
So it's
Yes.
plus 4 Vx, absolutely right. And then what's our last term here?
It'd be minus that Vx right there after the 4.
Yep, so minus Vx because we see that negative polarity terminal first. All right. So we have one equation and two unknowns, right? We don't know what V30 is and we don't know what Vx is. While I'm at this, we can do a couple of simple simplifications here, right? So just for the sake of cleaning things up, I'm going to have the V30, 4 Vx minus 1 Vx to me looks like 3 Vx. And then I'm going to move that constant term of 60 volts over to the other side of the equal sign. Is everybody okay with my algebra that I did here?
Yes.
All righty. So we, as I said a moment ago, we have one equation, but we have two unknowns. So what we're going to do is we're going to bring Ohm's law in to help us figure out how to solve for that current IA, right? Because we have resistors and we have the voltage drops across the resistors specified, we can now use Ohm's law to put both of those resistor voltage drops in terms of that current IA. So using Ohm's law, we can actually write two more equations here, right? So I can say that the voltage V30 is simply 30 ohms times the current IA, because the current IA is flowing into the positive polarity terminal of V30. So I use the positive sign representation of Ohm's law. Similarly, I could say that the voltage Vx is going to be 15 ohms times IA. And because the current is flowing into the negative polarity terminal, I need to put the negative sign out front. And so that's how I write my Ohm's law equations, and then I can substitute both of these into this KVL equation. And what that's going to give me is 30 ohms times IA minus 15 ohms times IA is equal to 60 volts, which looks like 30 minus 15 is 15 IA. Excuse me, 30 minus 15 is 15, so I'll have 15 IA is equal to 60, or IA is equal to 60 volts over 15 ohms is equal to 4 amps. Everybody okay with the algebraic substitutions that I've made here?
Yes, and just for the Ohm's laws, there were a few different versions of the same statement. Do I just kind of get used to which one to use when?
Absolutely. So let me scroll back up here really quickly. For the Ohm's law stuff, these two, actually, let me expand this to include the picture because it's important. These two representations are the ones that you're going to use the overwhelming majority of the time. Okay. They are also happen to be the ones that I used as well, right? So if we look at the circuit diagram that we were just dealing with, in one case for the voltage drop V30, our current was passing through the positive polarity terminal of our resistor, which is why I used this expression. When we were calculating, or when we were applying Ohm's law to figure out what was going on for the voltage drop Vx, the current IA was flowing into the negative polarity terminal, which is why I used this formulation. So as long as you understand that when the current is flowing into the positive polarity terminal, Ohm's law gets a positive sign, and when the current is flowing into the negative polarity terminal, Ohm's law gets a negative sign, it's really only one equation that you need to use and need to remember.
Okay, that makes sense. Thank you.
No, questions are great. So I'm pleased that you guys are engaged. All right, so we have found out that IA is equal to 4 amps. Let me see what's going on in chat here. You know what? You are absolutely correct. Mr. Lewis mentioned the fact that I don't just have Vx, I have 3 Vx. So let me modify this really quickly, and thank you for catching that mistake. So I should have minus 3 here. So 30 minus 45 is going to look like negative 15, which is going to put a negative sign here. Thank you very much for that, Mr. Lewis. You're absolutely right. I forgot to include this 3 right here when I was doing my algebraic substitutions. By the way, it should be very obvious. I'm going to make mistakes. If anything seems fishy, by all means, stop me and correct me. I would much rather take care of the mistakes as they show up than try to hunt them down towards the end, because that's a little bit harder to do. So I don't take any offense to you guys telling me, hey, I think you made a mistake. All right, so with that correction, are we all in agreement that IA should be negative 4 amps?
Yes.
All right. So now let's talk about how we can use Kirchhoff's voltage law to find this quantity VB. I'm going to do it over here on the right-hand side so that we can still see our schematic diagram. So I have 2 choices here for the path that I can do to find VB. I can either do this path, which is I'm going to label in pink, so I can start from the bottom left-hand corner here, go through this resistor, down and like so. Or I could start here, go around like so. So this is what I was talking about with a closed path, okay? As long as I start my Kirchhoff's voltage law equation and end my voltage law equation at the same node, I have formed a closed path. It does not remotely matter whether or not current is capable of flowing through all points of these paths, okay? So I'm perfectly okay with writing a KVL equation where I'm taking the voltage drop across this, what I'm going to call an open circuit, or this big gap in the middle. So I'm going to write the KVL equation for both paths, and we are going to find that they're going to give us the same answer, okay? So KVL at the left-hand path is going to look like negative 60 volts plus V30 plus VB is equal to 0. So from this, we could say that VB is equal to 60 volts minus V30. And V30, if you recall, is 30 ohms times IA, where IA we found to be negative 4 amps. So that 60 minus negative 120 to me looks to be 180 volts. If I write a KVL equation around the right-hand loop, the right-hand path, what I'm going to, sorry, let me see what's going on in chat here. Once we know the current IA, both ways are equally as easy, in my opinion. And in fact, we can't do this until we know the current IA. There's, I guess, going to be slightly less substitutions with the path that doesn't contain the dependent source, but in the grand scheme of things, it's not going to matter at all. So around our right-hand path, we have negative VB plus 4Vx minus Vx is equal to 0. So we could rewrite this to say that VB is equal to 3Vx. So that's going to be 3 times 15 ohms times our current of negative 4 amps. And then since Vx is negative 15 ohms times IA, I need another negative sign out here. So that is negative 3 times 15, which is 45, times negative 4, which comes out to be positive 180 volts. So it literally did not matter which path we chose. Either one of them gave us the same voltage, VB, that we were trying to find. So sometimes students are a bit incredulous about being able to write a KVL equation using the voltage drop across effectively nothing, because there's no component connecting this node and this node that we're taking the voltage drop against, or excuse me, the voltage drop across. To that I say, think about it like you were taking the voltage drop between 2 points in a circuit with a multimeter. It doesn't necessarily have to be over, a single resistor. It can be over some combination of circuit elements. And that's exactly what we're doing here. As long as we can identify 2 different points in the circuit, and because voltage is simply the potential difference between 2 points in a circuit, we should be able to use KVL to determine what that voltage drop is. All right, so We've talked about Kirchhoff's voltage law a bit here. We've worked a couple of examples. I've made a mistake. Does anybody have any questions before we move along to Kirchhoff's current law?
I guess the only thing is we're calculating the voltage drop, but you could do that between any 2 points with this method, right? And which I kind of expect. For like,
Absolutely, yes.
okay, it's just a property of KVL.
Exactly right, yes. Well, it's really a property of voltage as the potential difference between 2 points. KVL is just a good way to solve for voltages.
I see. Okay.
Mr. Lewis asked where this negative sign, let me point it out here really quickly. At least I believe this is the one that he's referring to, but where this negative sign came from. This negative sign here is this negative sign here. So since our current IA is entering the negative polarity terminal of the voltage Vx, we need to include that negative sign in our Ohm's law equation. So let me squeeze it in right here, right? So I have 3 times negative 15 ohms times my current IA. And that IA is just this negative 4 amps here. And so that's why those 2 negative signs wind up canceling each other out. And we get positive 180 volts in each case. No problem. Happy to explain stuff. All right, any other questions about these examples or Kirchhoff's voltage law before we move on to Kirchhoff's current law? All righty, let's take a look at KCL.
You
So-
said this is all like German engineers that discovered all this.
I'm not sure where Kirchhoff was from, but resistance was George Simon Ohm, who was a German physicist in the 1800s. The units of conductance are named after a German man, last name Siemens. I don't know that he discovered anything per se, but that's who the unit is named after. But I'm not sure where Kirchhoff hailed from.
All right.
All right, so there are actually several different ways that we are going to apply Kirchhoff's current law. They all are really the same thing, just from looking at things from slightly different perspectives. So I'm going to draw a little something here that's going to help us figure out how to apply KCL. So I'm going to have some node here in the center, and then I'm just going to draw a series of wires stemming out from this node. And we are going to assume that this is connected to some part of a larger circuit so that we have paths for current to flow through. I'm arbitrarily going to assign directions for the currents that are flowing into and out of this node. So let's say that this current I1 is flowing into this central node point. Let's say that I2 is flowing out. I3 will also flow out. I4 will flow in. And I5 will flow out. So we have a node, and then there are multiple currents flowing into and out of said node. So the first way that we're going to look at Kirchhoff's current law is the way that it was probably taught to you in the Engineering 120 series. And so that formulation of Kirchhoff's current law says the total current flowing into a node must equal the total current flowing out of that same node. So if I were to write a Kirchhoff's current law equation for this thing, right here, KCL, I1 is flowing in, so the left-hand side of the equal sign is going to be my currents flowing in, and the right-hand side of the equal sign will be my currents flowing out. I2 is flowing out, so I'm going to put it over here. I3 is flowing out, so I'm going to add I3 to I2. I4 is flowing in, so I'm going to add it over here. I5 is flowing out, so I'm going to add it over here. And I have correctly applied KCL to this system. The currents flowing in, I1 plus I4, have to equal to the currents flowing out, I2 plus I3 plus I5. Everybody okay with this?
Yes.
All right. So now let's look at the second way that we can express Kirchhoff's current law. This formulation is the total current flowing into a node must equal to 0. So this is not saying that I1 plus I4 is equal to 0. Instead, what we're going to do is we're going to represent currents I2, I3, and I5 as if they were flowing in. So I1 is flowing in, so it gets a positive sign. I2 is flowing out, which means negative I2 is flowing in, because as we discussed in our last class meeting, if we want to change the direction of a current, we simply change the sign on its magnitude, right? Since I3 is flowing out, we change the direction by including a negative sign. I don't know why my stylus isn't writing, sorry. I4 is flowing in, so it's going to get a positive sign. I5 is flowing out, so it's going to get a negative sign. And then we set all of these equal to 0. Mathematically, this expression is exactly the same thing we have above. We just moved everything from the right-hand side of the equal sign over to the left, right? So it represents literally the exact same mathematical expression, just from a slightly different perspective. Our third formulation of Kirchhoff's current law is effectively the same thing, except we're going to say that the total current flowing out of a node must equal to 0. So looking at KCL from this perspective, negative I1 is flowing out, positive I2 is flowing out, positive I3 is flowing out, negative I4 is flowing out, positive I5 is flowing out, set that equal to 0. And it's the same thing as our last expression, except everything is multiplied by a factor of -1, because we're choosing the opposite direction to effectively be our reference. Okay, so let's apply Kirchhoff's current law to an actual circuit now. So this is the circuit that I want us to analyze here. We have 8 amps of current being supplied by a current source flowing up. We have an unknown resistor here. The current flowing through this resistor, excuse me, is 1 amp. We have a current flowing down here. And then we have another resistor whose value doesn't particularly matter. And I'm going to define this current Ix to be up. And we're going to try to solve for that current using Kirchhoff's current law. Okay. So once we have a lot of practice with this, it's going to be kind of second nature to do it. But since we're learning things, once again, I'm going to be very methodical in my approach. Just as a quick aside here, this is an example of a single node pair circuit. And all that means is that everything is connected in parallel. I'm telling you the definition for single node pair circuit and single loop circuit because you're going to see things in your homework assignments where it's going to look really terrifying, but it tells you, oh, this is a single node pair circuit, and that gives you a very strong hint. In fact, it's not a hint at all. It's explicitly telling you that actually everything is connected in parallel. But anyway, so we're going to use Kirchhoff's current law to solve for this current Ix. But in order to do that, we need to make a couple of decisions, right? So one thing that I'm going to do here really quickly is I'm going to identify my nodes. This isn't particularly necessary for a circuit this simple, but we are going to make a distinction here. So I've labeled my top node in red. And then let's do this Christmas style and make my bottom node in green. Okay. So we apply Kirchhoff's current law at a node. So I want you guys to tell me if we're going to apply it at the top node or the bottom node.
Outside of just picking one at random, is there a reason I would want to pick one over the other?
Nope, it's completely random. Doesn't matter. It's entirely arbitrary.
Let's do top.
Top. All right. So one person said top, the other person said green. I saw top first, so we'll do that one. So Dave, because I'm not using your suggestion for green, could you tell me which formulation of Kirchhoff's current law you want us to use? 1, 2, or 3? Number 1 all day. All righty. So I'm just going to put top, comma, number 1. So we are going to use the number 1 formulation. Currents flowing in is equal to current flowing out at the top node. Okay. So my 8 amps of current from my leftmost source is flowing in. So I'm going to put it on the left-hand side. Put my equal sign here in the middle. The 1 amp is flowing out. So it's going to go on the right-hand side of the equal sign. My 2 amps is flowing out of the top node. So it's going to go on the right-hand side of my equal sign. And the current Ix is flowing into the top node, so it goes on the left-hand side of my equal sign. And now I can algebraically manipulate this to find that Ix is 1 amp plus 2 amps minus 8 amps is negative 5 amps. And I have used Kirchhoff's current law in order to solve for that unknown current. Fairly straightforward. If we had chosen to do KCL at the bottom node, we would get the exact same result. If we had chosen to use formulation number 2 or formulation number 3, we would get the exact same result. Does not matter which node we apply it at or which formulation of Kirchhoff's current law we use, we'll get the same result all day long. Okay. I will say that when we start doing nodal analysis, which if memory serves me right, will be sometime next week, we're going to wind up using formulation number 3 when doing nodal analysis. It's not required, but this particular formulation will give us the least amount of negative signs. And I know for me personally, the smaller the amount of negative signs there are, the less likely I am to make a mistake. So that's why I particularly use formulation number 3 when I do mesh analysis. Excuse me, nodal analysis. So anyway, all right, let's work another example problem here. Once again, we're going to make things a little bit more complicated so that we can tie in Ohm's law and see how it can be used to aid in our circuit analysis. So let's start with this circuit. Let's say that we have a 5 amp source here. Let's make this an 8 ohm resistor. A 1 amp source here. Let's make this a 10 ohm resistor. A 6 amp source here. And what we are trying to solve for is the voltage drop in our circuit. Let me do it in blue. Let's make it interesting. With this particular polarity. So before we apply Kirchhoff's current law to this circuit, I want to show you guys something here. Okay. So whenever we have a single node pair circuit where everything is connected in parallel, it turns out that the same voltage drop occurs over all of the elements connected in parallel. And we can prove that very easily by writing a Kirchhoff's voltage law equation, right? So for example, we do this in purple. If I called this the voltage drop across the 5 amp current source, and I'm choosing the positive polarity on bottom so that it will have the exact same polarity as the voltage Vx that I've defined. And I write a KVL equation around this path. What I will see, I'm going to do it up here because I'm going to wind up erasing this in a moment so that it's not so busy, is that positive V5 amps minus Vx is equal to 0, which means V5 amps is equal to Vx. So those two voltages are identical. Every voltage in this circuit, or every voltage drop across any element in this circuit with the positive polarity on bottom, will be the exact same thing as Vx, because it doesn't matter how I write my Kirchhoff's voltage law equation, I'm always going to get this exact same result. If I happened to define a voltage with the opposite polarity, so for example, the voltage drop across my 6 amp source, if I wrote my KVL equation around this loop, I would see that Vx plus V6 amps is equal to 0, which means V6 amps is simply negative Vx. So it's still the same magnitude, but the sign is different because the polarities are opposite each other. Okay. So just as a quick recap here, anytime we have things connected in parallel, they must have the same voltage drop over them. If the positive polarity terminal is on the same side, it is the same sign. And if the positive polarity terminals are on opposite sides of each other, then we simply include a negative sign. Okay. Anybody have any questions about that before we move on and actually work the problem that I wanted to? All righty. So back to the question at hand. We have a single node pair circuit. So we're going to apply Kirchhoff's current law. So are we going to apply KCL at the top node or the bottom node?
Top.
Okay. And let's use a different formulation of Kirchhoff's current law just for the sake of using one of the other ones. So are we going to use number 2 or number 3?
2.
What, could we use 3 since you said we might use it later?
Sure. Okay, so let's do number 3. All right. So KCL to top node using number 3. So what this means is that any current that is leaving the top node will get a positive sign, and any current that is entering the top node will get a negative sign. So starting with the 5 amp source on the left, that one is entering the top node, so it's going to get a negative sign. Now we look at our 8 ohm resistor. There is no current direction specified, so we need to choose one. So just for the sake of argument, I'm going to choose this current direction as down. I'm going to call this I8. And for the other resistor, I'm going to choose it as up. So I'll call this I10. So that we'll get to use Ohm's law in both ways. All right. So let's see, I8 is exiting the top node, so it's going to get a positive sign. 1 amp is exiting the top node, so it is going to get a positive sign. I10 is entering the top node, so it gets a negative sign. And 6 amps is entering the top node, so it gets a negative sign. And we set this equal to 0, and we can do a couple of simplifications here. So I see that I have a positive I8 and a negative I10. Let's see, I'm going to have that is equal to 5 plus 6 minus 1. So that's 11 minus 1 is 10 amps. If my mental math is correct, if anybody wants to or needs to correct my algebra, please do so. But I believe I got this right. Yeah. The I8 has a positive sign because I left it on the left-hand side. I10 has a negative sign because I left it on the left-hand side, moved all the constants to the right. So that means the signs of all the constants changed. So 5 plus 6 minus 1 seems like 10 to me. Okay, I believe I got this right, and none of you are telling me that I didn't, so let's move on.
It checks out with me too.
Good deal. So what we're going to do now is we're going to use Ohm's law, and we're going to express the currents I8 and I10 in terms of that common voltage Vx, right? So just as a quick aside here, Ohm's law rewritten as the one that you guys are probably familiar with, V is equal to I times R. So since we're having currents, I'm expecting things to be of the form I is equal to V over R, where we need to remember to pay attention to if the current is flowing into the positive polarity terminal or the negative polarity terminal. Okay. So how am I going to express I8 in terms of Vx?
But wouldn't we solve for Vx first? And then we would divide it by the resistance?
So we can't solve for Vx yet because we don't know literally any voltages whatsoever. So that's what we're trying to figure out effectively, right? So we have our KCL equation, and it currently has two unknowns for that one single equation. What we're going to do is we're going to use Ohm's law in order to express I8 and I10 in terms of that voltage Vx, so that we wind up having one equation that only depends on Vx that we can solve for Vx with. So what I'm trying to get you guys to do is to use Ohm's law and tell me how to write I8 in terms of Vx.
Okay, would it be I equals 8 ohms equals V over, and then the resistance, we would need to get the resistance.
Wouldn't you have to take the average of both resistors since they're in a parallel?
No, because I want the current that's just flowing through the 8 ohm resistor.
Oh.
So I literally circled the Ohm's law relationship right here, right? So we're going to have Vx in the numerator because Vx is the voltage that's common to everything in this circuit because all of the elements are in parallel. The resistor value is 8 ohms because it's an 8 ohm resistor. It was specified. But what we need to observe is that the current is flowing into the negative polarity terminal, which means we need a negative sign here. For I10, we would have Vx divided by 10 ohms, but the current is flowing into the positive polarity terminal first, right? So here's that current I10, another way to look at it. It hits the positive polarity terminal first and then exits the negative polarity terminal. So this one gets a plus sign. Okay. Once again, whenever we're dealing with Ohm's law, let's look at what's going on in chat. Okay, so you guys are just talking about the ICA there. Okay, sorry. So whenever we're applying Ohm's law, whenever the current flows into the negative polarity terminal, we need a negative sign indicated here. And whenever the current is flowing into the positive polarity terminal, we wind up using a positive sign out front. So I just want to be really, really clear about that because it's going to show up over and over and over and over again. And it's one of the places where a lot of mistakes can happen. So I'm just trying to beat that horse to death. All right, so if we substitute in the relationships, we have I8, so that is negative Vx over 8 ohms minus I10, so that's minus Vx over 10 ohms is equal to 10 amps. Doing a little bit of algebra here. My stylus will write. There we go. I'm just going to factor out Vx, and so that's going to look like -1/8 ohms minus 1/10 ohms is equal to 10 amps. And then I'm going to solve this, which I'm not comfortable doing in my head right now because I haven't done enough mental math in the last few days to make sure my brain's working properly. So I'm just going to put this in my calculator. 10 divided by -1/8 minus 1/10. I get -400/9 volts. Or for those of you that like decimals, -44.4 repeating volts. So in this example problem, we applied Kirchhoff's current law at the top node using formulation number 3. I intentionally chose different directions for my resistor currents to force us to think about what sign our Ohm's law representation needs to have. And then we did a little bit of algebra and solved for that unknown voltage Vx. Okay. So we've now talked about Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. Does anybody have any questions?
No, I just think like practice, but you said that, so but that's all.
Yeah. Okay. I'll stay on Zoom just in case anybody has any questions. I do want to mention a couple of things here very quickly, though. On Thursday, I will be participating in the College of Engineering and Sciences freshman orientation, which means I probably won't stay on Zoom until 4. After we wrap the lecture up and I answer any questions that you guys may have, I'll probably close the Zoom meeting and then head back over to the IESB to help out with the orientation. On Monday and Tuesday of next week, I have a workshop that I have to attend that lasts until 3 p.m. So we have 2 options. And it lasts until 3 p.m. on both days. I can either start my lectures late at 3 p.m. or I can give you guys access to videos of me teaching the material in a different quarter, and then you guys can watch those videos as the lecture, and then I'll be on Zoom at 3 to answer any questions that you might have. Do you have any particular preference? Like, do you want me to give the lecture at 3 or answer questions at 3?
But personally, it seems like uploading the video and then being around at 3 to answer questions, kind of like it's the best of both worlds, and it helps you out and it helps us out. That seems obvious to me, but
well, you're saying that, and then the other person that's responded wants the exact opposite. So
How about you upload a video and then you lecture later?
well, so technically speaking, the videos are already up. They've been up for months because I record everything that I've done since COVID. But I can provide you the links or whatever, and then I'll just give the lecture at 3. Okay. So I'll send an email out to you all to remind you that the lecture isn't going to start until 3 p.m. on Monday and Tuesday of next week. And I'll intend on giving the lecture at 3 and try to wrap things up by, say, 4:15 or 4:30 so we don't go too wildly long after when class is supposed to end.
That works.
Are you going to post the modified schedule on Moodle?
No, I'm not sure that I'm following. I'm just going to send you guys an email to let you know that those lectures are going to start 1 hour later.
Okay, that's a better.
Okay, change of gears. Is that okay?
Absolutely.
Okay. So I wrote a few things down. So the last homeworks, the homework one. I mean, so two things. Level of difficulty. I know it's the first homework, so I'm kind of taking it with a grain of salt. But as far as difficulty goes on the exam, how comparable are they?
So trying to think of how to put this without sounding like more of a jerk than usual.
I'm okay. Sound like a jerk. I'm okay with that.
No, so I don't particularly like most of the homework problems that are part of web work, but I have not found the time to learn how to program in Perl to write my own web work problems. So with regards to material to study for the test, if that is your focus, the in-class assignments and the old exams that I have posted would be a good representation of what you should expect on the test because I wrote all of those questions. There are some homework problems that I think are good problems, and typically speaking, I tell you, hey, I think this is a good problem, expect something like this on your exam. We are about 2 weeks from me saying that.
Okay.
I do believe that it is important that you guys do the homeworks because it's practice.
Yeah.
But if you're specifically looking to study for one of my tests, I feel like looking at the older tests that I have written is probably the better way to do it. And which is why I give you guys, I think, three or four examples of old tests, so that you can get as much practice as I think you can tolerate in order to study.
Okay, that's
What
great.
form? What format is the exam in?
So the exam is going to be very similar to the practice tests that I've uploaded, except that it will be done online on Moodle using the Respondus lockdown browser. So effectively what that's going to look like from your end is you're just going to be able to see one problem at a time per screen, and then you'll move on to the next screen. The same circuit schematic diagram will be used for multiple circuits, or excuse me, for multiple problems, much like it is in the exams that you would print out or something like that. But I make sure to include the same picture on each of the problem screens on Moodle, so that it's very obvious you're supposed to be using this particular circuit for this particular problem, so that there's no confusion. It's not like these four problems are going to use this one circuit diagram, and then you only see the circuit diagram once. It'll be up there for every problem associated with that particular diagram.
All right. Do you have an estimate on when you're going to upload that what's it called? The trial run for Respondus for us to play with?
I'll try to get that done tomorrow because I only have one class to teach tomorrow. So I'll try to get that.
All right, sounds good. Because I'm eager to play around with it.
Oh, for sure. Yep, I'll get it up. In fact, well, I'm trying to figure out where the hell my post-it notes are in my home office. I think I have some in my desk drawer. I was going to make myself a note to remember to do it really quickly and to stick it on my monitor.
And could you scroll all the way to the top of your PDF file there? I want to check something.
Sure.
Oh wow, we actually so I'm using the same exact engineering paper template as you on my tablet when I'm taking notes. I think that's really funny.
Yeah, probably
Did you get
found,
yours from Google as well?
I found it maybe 4 or 5 years ago, maybe, and I can't do math on not engineering paper. So that's why I can't use OneNote. I need it to have like the right sections and everything. Dave, yes. So explain the polarity on the 8 ohm resistor. Let me scroll back down to that. Okay. So the current IX is flowing down. Let me do it in purple here. Change color. Down through the 8 ohm resistor like so. It hits the negative polarity terminal first, which is why we get a negative sign here. Similarly, if we look over here at the current flowing through the 10 ohm resistor, erase, there we go. I don't know why this is being difficult and not writing, there we go. It hits the it hits the positive polarity terminal first as it flows through the 10 ohm resistor, which is why it gets a positive sign. Was that sufficient, or were you asking a different question than I misinterpreted? Yes, it was sufficient, or yes, I answered the wrong question. Okay.
Okay, I only have one more. Formula sheets. Can we get one? Can we like make one? And is it allowed on the exam?
No.
Okay.
You can make one all day long, but it is not allowed on.
Okay. All right.
Yep.
That's all I got.
All righty.
Michael, you still planning on meeting later?
Yeah, absolutely. Any idea what time you're up for?
Yeah, I think so. Let's plan for 6:30 to 7. The little one goes down at 6:30, and so I'll be like completely free then.
I love the way that the little one goes down.
A little guy.
Oh yeah. Do you want me at the engineering building?
What? Huh? Were you
Are
asking?
you meeting in person? Okay.
Oh no, I'm in Houston.
No. Oh, okay. You're in Houston.
Yeah.
Okay. I think we'll be doing this over Discord then.
Yeah, that's okay with me. I can get a whiteboard set up. Not that we would need it. We might, but or we can do it on here too. I've been pretty successful with it so far.
Yeah, I have a tablet at my disposal with Samsung Notes and the stylus, so I'll be able to open my stream up on there.
Perfect. Okay. Okay. All right. Well, I'll see y'all later. Thank you, Dr. Hartman.
See you then.
All right.
You have a good day, Dr. Hartman.